In this presentation, I am going to explain insulated gate bipolar transistor IGBT. Basic structure of IGBT. What are the static characteristics and the switching characteristics of IGBT? That will be explained in this presentation. Insulated gate bipolar transistor or IGBT, and this IGBT has got the advantages of both MOSFET and BJT. As you know that MOSFET has the switching loss is less for the MOSFET, but conduction loss is more. But in BJT, switching loss is more and conduction loss is relatively less. Therefore, in IGBT, as it has got a high impedance like MOSFET and low on-state power loss like BJT, or IGBT has got the advantages of MOSFET and BJT like switching loss is less as well as the conduction loss is also less. Switching loss is less like MOSFET and conduction loss is less like a bipolar junction transistor. Therefore, IGBT has got the advantages of MOSFET and bipolar junction transistor. Symbolically, this is an IGBT in which it is a 3-terminal device, and one terminal is called the gate terminal, and another one is called the emitter, and this is the collector. Or this part is similar to bipolar junction transistor, but this is similar to the MOSFET. Now, this is the structure of IGBT, in which it is a p-type structure. P-type substrate is there, over which it's a n minus diffuse, then again p and n plus, and here it is again this the 3-terminal device as MOSFET here, and here it is the emitter terminal, and this is also emitter terminal, and here above this one there is a silicon dioxide. It is a insulating material is there above this n plus material, semiconductor material. This is insulating material, and from this one this is connected to the output terminal like emitter, and this is also emitter terminal through the metallic contact. These are the metallic contacts, and this is also metallic contact, and this terminal is called the gate, and these two terminals are the emitters. These emitters are shorted, and here this the p-type substrate that is through a metallic contact that is taken outside, this is called the collector. Therefore, this is collector, and these two terminals are called the emitter, and this is called the gate. And we are applying a positive voltage at the gate terminal with respect to the emitter. And when a positive voltage is applied, then electrons will be inducing on this between this n plus and n minus, that will be shorting this one. And here an IGBT is constructed virtually in the same manner as the power MOSFET. The major difference is the substrate. The substrate here in a MOSFET, if you see that this is the MOSFET here, this is a p-type substrate, and here these are the n plus, and this is the drain terminal, and this is the source terminal, and this is the gate terminal. Therefore, here the n plus layer substrate is at the drain in power MOSFET. Therefore, in power MOSFET, and now it is being substituted in IGBT as the P plus layer. Therefore, in IGBT, it is substituted as the collector terminal. That collector terminal is connected to the p-type substrate, and the same counterpart, the drain here, the drain terminal is equal to n plus layer in the MOSFET. Therefore, this n plus layer is connected to the drain terminal in the MOSFET. Its counterpart, just like collector terminal, that is connected to the p-type substrate, p plus substrate. Therefore, this is the basic structure of a IGBT, and here externally the collector terminal is between the collector terminal and here the emitter terminal, the load is connected, and with a source, that is VCC is there, and this is the load is being connected. Continuing the structure of insulated gate bipolar junction transistor IGBT, and this is the structure of IGBT. And when the gate is made positive with respect to the emitter, that is, this is the gate terminal and these are the emitter terminals. When gate is made positive with respect to the emitter terminal, and when this voltage is more than the threshold voltage, that is of the IGBT, that is above which that the channel will be establishing. Therefore, if this voltage is more than the threshold voltage of IGBT, an N channel is formed in the P region. Therefore, in the region P region, here in the region P, N is inducing here because of a positive voltage that is applied between the gate and emitter. And this N channel, that is the N channel in the P material, that N channel short circuits N plus and N region. That will be shorting this N plus as well as N minus region, that will be shorting this one. And an electron movement in the N channel causes a substantial hole injection from the P plus. From the P plus, a substantial holes are coming as the electrons are moving, and from the P substrate layer into the epitaxial layer. Thus, this will be forming a current in the circuit. Therefore, as the electrons are moving here, to that one the holes will be injected from the P-type substrate, that will be causing a current in the circuit. Therefore, when a voltage is applied here electrons are established, channels being established or inducing here between N plus and N minus, that will be short circuiting that, and to that region holes will be injecting from the P-type substrate, that will be constituting the current. The layer P plus NP, that is the layer P plus and N minus and P, these three layers, that will be constituting a PNP transistor. Therefore, that will be constituting a PNP transistor with P plus as the emitter and N minus as the base, and P as the collector. Therefore, it is equivalent. It can be analyzed as it is a PNP transistor on this side, and other one, that is the layer we get N minus P N plus, that is N minus P N plus. That will be constituting another. It is a P, that will be constituting a NPN transistor. This will be constituting a NPN transistor, and with N plus as the emitter, P as the base, and N minus as the collector. Therefore, these three will be constituting a PNP transistor. Other will be constituting a NPN transistor, or it is a PNP and NPN transistor inside the structure we can analyze like that one. Therefore, N serves as the base for a PNP transistor and as a collector for a NPN transistor. Similarly, P serves as a collector for a PNP transistor and base for a NPN transistor. Therefore, this is the internally you can analyze as a two transistors. One is a PNP transistor, other is a NPN transistor. Therefore, this is the structure of a IGBT, and this is the internally it is as if two transistors, PNP and NPN. Continuing the insulated gate bipolar transistor IGBT here, as already we have seen, this is the structure of IGBT, in which P-type substrate is the N minus material, and here N plus and P, and here this side you can consider this P-type as well as N minus and N plus, that is P plus, N minus and P, that will be constituting a PNP transistor. Another one N plus and P and N minus, that will be constituting a NPN transistor internally, and it can be represented as this is the equivalent circuit of a IGBT, in which this is the gate terminal, just like a MOSFET, like it is a gate terminal is there, and here the terminals collector and base. This is the collector terminal, and collector and emitter, and this can be considered as these two transistors PNP and NPN can be connected like this one. Therefore, this is the what is called the equivalent circuit, and it can be seen that the two transistors PNP and NPN transistors are connected as shown in the figure. Therefore, this is the equivalent circuit of an IGBT, in which this is the gate terminal, and these are the two transistors inside that one, a PNP and NPN, and the symbolically it is represented as like this one. It's a three terminal device in which this is the gate terminal, other two terminals are the collector and emitter. This is the collector and this is the emitter terminal. This is the emitter terminal and this is the collector terminal and this is the gate terminal. So this is the symbol for an IGBT and this is the equivalent circuit. Coming to the IGBT characteristics, that is static characteristics, output characteristic this one. And to find out that one, this is the IGBT in which the voltage is input voltage is applied between the gate and emitter, that is VGE is the input voltage, and series to the collector a resistor is connected, to that one a voltage VCC is applied and that is given to the emitter. Therefore, this is the output side and this is the input side. Therefore, here unlike the IGBT, it is a voltage control device. We are varying the voltage between gate and emitter. In IGBT, in bipolar junction transistor, we have been in BJT, it is a current control device, and IGBT is a voltage control device like MOSFET. And here we are varying the voltage between gate and emitter. But in bipolar junction transistor, we will be controlling the base current. Therefore, here the output characteristic is a characteristic that depicts the variation of the collector to emitter voltage VCE versus IC. Just like a BJT itself, the variation is same, VCE versus IC, but the variable that is changing here, it is equal to it is the gate to emitter voltage. That is, for different VGE gate to emitter voltage, we are plotting the collector to emitter voltage versus IC. For this is the output characteristics for an IGBT, but in this case of bipolar junction transistor, it is VCE versus IC for different IB. Therefore, it's a current control device, but IGBT is a voltage control device in which you will be varying the voltage between gate and emitter. Thereby, you can change the shift the curve like in the output characteristics. Therefore, this is the output characteristics of an IGBT, and the forward characteristic is similar to bipolar junction transistor. Only the variable it is equal to gate to emitter voltage, unlike base current. And this is called the transfer characteristics. And one more thing is that this is the reverse characteristics of the IGBT and this is the forward characteristics, and this is called the transfer characteristics. Transfer characteristics, it is a plot of the input voltage is equal to gate to emitter voltage. Therefore, VGE versus what we are observing is the output is the collector current. Therefore, VGE versus IC, that plot is called transfer characteristics. Once the gate to emitter voltage is less than the threshold voltage, if VGE is less than the threshold voltage, then the IGBT is said to be in an off state. For once this voltage is going less than the threshold voltage, that is getting turned on. Or in order to turn on this device, this voltage should be more than the threshold voltage, Therefore, this is the transfer characteristics. That's the relation between the output, that is the collector current, and input, it is the gate to emitter voltage. Therefore, this is the, and one more thing is that in the reverse side, in here you can, the third quadrant, we can see that one, when it is here, when a voltage is, the reverse collector to emitter voltage is in reverse here, there will be leakage current, and until this point, then breakdown is being taken place. Therefore, the output characteristics of an IGBT is the plot of the collector current versus the collector to emitter voltage, collector current versus collector to emitter voltage, VCE, for various value of gate to emitter voltages. For various value of VGE, we are plotting VCE versus IC. This is the output characteristics of a IGBT. And in forward direction, the shape of the output characteristics of IGBT is similar to bipolar junction transistor, but the controlling parameter is VGE. That is the controlling parameter here is equal to gate to emitter voltage. But in bipolar junction transistor, the controlling parameter is the input base current. Next, we are going to explain switching characteristics of IGBT. Switching characteristics of IGBT during turn on as well as turn off period, that will be explained. And here these plots are the variation of the gate to emitter voltage VGE then voltage, collector to emitter voltage, and the collector current. These are the three variables which is plotted. The variation of VGE versus time, the variation of collector to emitter voltage with respect to time, and the variation of the collector current with respect to time during the turning and turn off process. Therefore, this is the here at this instant we are this is the turning on process. The turning, we are applying the signal VGE at this switching signal is applied at this instant. Therefore, at this instant turning on process is taking place. Therefore, the turn on process or turn on time is defined as the time between the instant of forward blocking to the forward on state. That is instant of forward blocking to the forward on state. This is the before this one it was in forward blocking state, and here at this instant, if you know, here it is taken as the forward on state, or the total time for this one we call it as turn on. That's called the turning on process, and that time is called the turn on time. This turn on time, this from this one to this one, this turn on time constitutes two parts is there. One we call it as the delay time, that is this part is we call it as delay time, and the second part is called the rise time. Therefore, the total turn on time is the sum of two times. One we call it as the delay time, other one is called the rise time, and this is called the delay time and this is called the rise time. Let us see what is that one. Delay time, TDN, that is equal to time for the collector current, time for the collector to emitter voltage. That is here collector to emitter voltage is this one. The collector to emitter voltage to fall from VCE to 0.9 times VCE. That is this VCE, once we are applying the switching signal at this instant, the VCE is changing from, this is the, when it is turned off case, this is the voltage collector to emitter voltage when this switch is off. This, the time to change from this point to 0.9 times of VCE, this time is called the delay time. Or another way explain the same thing is that delay time can also be explained as the time during which the current rises. That is here the time for the collector current to rise from the initial leakage current, that is from this. So this is the initial leakage current. The time required for the collector current to change from the initial leakage current to 10% of the final value 0.9 I or to 0.1 or 0.1, so 0.1 times I or 10% of IC collector current. That time is also that is also we can call it as a delay time. Both are same. This is either the current has to change from the leakage current into the 10% of the final value, or the collector to emitter voltage is changing from its VCE into 90% of 0.9 times of VCE. Both are we call it as delay time. In this, VCE is the initial collector to emitter voltage, that is when it is off, what is the voltage that is equal to VCE, and similarly IC is the final value of the collector current. Therefore, this is called the turn on period. In that one, this is called the delay time. Another part of the what is the rise time. Therefore, what I explained is this delay time, and the rise time is what? The rise time, one thing is that we can say that one, it is the time to rise the current, collector current from 10% to IC or 0.1 IC to IC. What is that time? That we can call it as the rise time. Another way you can explain the same here also in terms of VCE, means the time required for reduce the collector to emitter voltage VCE from 90%, 0.9 VCE into 0.1 times or 10% of VCE. That also can be told as a rise time. Of that time we call it rise time, and the sum of the rise time as well as the delay time, that is the total turn on period. Therefore, when as you apply the switching signal at this instant, to get it turn on, it takes this much time. It is a summation of the delay time plus rise time. Thus, for the collector current, the rise time is equal to 0.1 times IC to IC. After time T on, collector current IC, that after getting turned on, the collector current will become IC. Once it is getting turned on, the collector current will become IC. This is the instant at which the transistor is set to be turned on. After that one, collector current will be IC, and the collector to emitter voltage will be falling to the VCE side. The collector to emitter voltage will be falling to VCE. That is, during the conduction of the device, the whatever the voltage across collector to emitter, that is called VCES, or that is called VCE saturation. That much voltage will be there. This much voltage will be dropped between collector to emitter as it is conducting. Therefore, the total turn on time is the summation of delay time TDN plus the rise time TR. Continuing the switching characteristics of IGBT, that is already previous slide I explained the turn on process. It is a sum of delay time plus rise time. During the turn off process, same thing we have to define what is the off time period. Therefore, here it is turning off mechanism happens, starts from this instant, and that also constitute of different times are there. And the turn off time, it is a sum of three portions are there. One we call it as delay time TDF plus initial fault time TF1 and plus final fault time TF2. Therefore, the total turn off period is a summation of delay time TDF plus TF1 plus TF2. Now, let us see each one. What is that one? Delay time TDF during the turn off process, it is the time during which the gate voltage falls from VGE to VGE threshold voltage. That is, here this gate to emitter voltage, here it takes certain time to change from this VGE, that is when it is on process, what is that VGE, and to reduce that voltage until VGE threshold voltage, until this one, this time we call it as, that is for gate emitter voltage to change from VGE to VGE threshold value, that is called, that can be called as a TDF or collector. Or another way we can, same thing we can explain another way here, regarding the collector current. The collector current will become, that is collector current falls from IC to 0.9 times IC. That is also we can say that collector current is changing here, collector current falls from IC to 0.9 times IC. TF1, that is the initial fault time, TF1 is the time during which collector current falls from 90% to 20%. From 90% to 20% change of current, from that is, from this is a 0.9 IC, from this one, this is equal to 20% of IC. How much time takes to change the collector current from 90% of this final value IC to the 20% of IC? This time we call it as the initial fault time TF1. 90% to 20% of initial value of IC, that is called TF1. And during TF2, here the collector to emitter voltage rises from VCE sat to 0.1 VCE. That is, during TF2, you can say that when the collector here VCE sat is changing from, until that VCE is equal to VCE sat, or VCE sat is changing from VCE is changing from VCE sat to 0.1 times VCE. 0.1 times VCE it is changing. That is VCE from here it is changing to 0.1 times VCE. That is this is the VCE here. This is changing, and this time equal to TF2 VCE. Therefore, TF2 can also be defined that it is a final time fault time is the time during which the collector current is falling from 20% to the 10%. From 20% it is falling to the 10%. This time can be defined as the TF2. Or the time during which the collector emitter voltage, that is the collector to emitter voltage, is rises from 0.1 VCE to the final value of VCE, or 0.1 VCE to the final value of VCE, or here 0.1 VCE is from here, 0.1 VCE to the final value of the collector to emitter voltage changing. That is the TF2. That is another page. TF2 is the time required for the collector to emitter voltage to change from VCE, the 10% of VCE, that is 0.1 times VCE, to the final VCE. That time we can call TF2. And the summation of all these three quantities, like fault time plus TF1 and plus TF2, that is what we call it as total turn off period. Therefore, the total turn off period is this one, which is sum of TF2 it is equal to TDF, TF1 and TF2, and the definition of each one is given here, and based upon the variation of the collector current or the variation of the collector to emitter voltage, it is defined, and the total fault time is the summation of these three quantity.